Here's something that should keep you awake tonight. 3.8 astronomical units from where you're lying right now, an object is glowing with perfect symmetry. Not approximate symmetry, not close enough. 94% perfect. Comets aren't supposed to look like this. They're supposed to be chaotic, asymmetric, messy balls of ice spewing jets in random directions. But 3i Atlas has apparently decided to ignore those rules entirely. The images from November 20th show something we've genuinely never seen before. A tailless, symmetric sphere of light, where a comet should be. Tonight we take you through a journey at the end of which you understand why some scientists are now quietly using the word engine, and why that possibility is both thrilling and terrifying. Let's settle in. On November 20th, 2025, something impossible appeared in the night sky. Amateur astrophotographers across the northern hemisphere pointed their telescopes toward a faint smudge in the constellation Pisces, stacking 20-minute exposures the way they always do, hunting for detail in the cosmos. What they found wasn't a comet. It was something we've never seen before. The images started flooding online forums within hours. People who'd been tracking this object for months, this thing we call 3i Atlas, suddenly saw their screens fill with something that didn't make sense. Instead of the expected chaotic tail, the messy spray of dust and gas that defines every comet we've ever studied, there was a perfect sphere. A glowing symmetric core that looked less like a dirty snowball hurtling through space and more like a miniature star wrapped in plasma. The symmetry measured out at 94% in some analyses. 94%. That's the kind of precision you'd expect from a manufactured object, not a natural body that's been tumbling through interstellar space for who knows how long. Let me remind you what comets are supposed to look like. They're messy. They're asymmetric by nature. As they approach the sun, solar radiation heats their icy surfaces unevenly. Jets of gas and dust shoot out from active regions on the nucleus, creating those iconic tails that stream millions of kilometers behind them. The jets fire in random directions because the surface is irregular, covered in craters and valleys and outcrops of different materials with different melting points. Comets tumble as they fly. They wobble. They're essentially cosmic debris, frozen leftovers from the formation of solar systems, and they look the part. Chaos is their signature. But this object, this thing that was supposed to be just another interstellar visitor passing through our neighborhood, has decided to break every rule we thought applied. The November 20th images show none of that chaos. What they show is a perfectly circular, intensely bright core surrounded by a symmetric glow. No tail streaming behind it, no obvious jets shooting in, random directions. Just this eerily perfect sphere of light, as if someone took a star and shrunk it down to a few kilometers across. Some observers are calling it a plasma star now, abandoning the word comet entirely. The term feels right when you look at the images. There's something about the quality of that light, the way it seems to radiate equally in all directions, that doesn't match what outgassing should produce. Plasma, that fourth state of matter, where electrons strip away from atoms and everything glows with electromagnetic energy, that's what this looks like. But comets don't generate plasma cores. They don't have the energy budget for it. Solar heating can produce some plasma in the coma, sure, but nothing that would create this kind of symmetric brilliance. So we're left with a mystery that splits into two very different paths. Either this symmetry is an artifact, some weird trick of optics or image processing, that's fooling us into seeing order, where there's really just the usual cometary mess. Or it's physical. It's real. And if it's real, we need to explain how a natural object, supposedly just ice and rock, can produce this kind of geometric perfection. The artifact explanation sounds reasonable at first. 20-minute exposures mean you're stacking hundreds of individual frames, aligning them, combining their light. Maybe the processing software smoothed out the irregularities. Maybe the rotation of the object during that exposure time blurred the jets into a symmetric halo. Maybe we're just looking at the coma from a particular angle that hides the tail behind the bright core. These are all possibilities that professional astronomers will tell you to consider before jumping to exotic conclusions. But the people who process these images aren't amateurs in the sense of being careless. They know their equipment, they know their software, and they're saying the symmetry is there in the raw data, before stacking, before heavy processing. Different telescopes in different locations are seeing the same thing. The optical explanation starts to feel thin when multiple independent observers are reporting identical geometric properties. Which brings us to the physical explanations, and this is where things get genuinely strange. If the symmetry is real, if this object truly has reorganized itself into a perfect sphere of glowing material, then we need a mechanism. Rapid rotation is the first candidate that comes to mind. Spin something fast enough and centrifugal force will distribute material evenly. Maybe Atlas is rotating so quickly that any outgassing gets spread uniformly across its surface, creating that symmetric glow. But the rotation rate required for this effect would be extraordinary. We're talking about a nucleus potentially several kilometers across, spinning fast enough to blur into a perfect sphere over a 20-minute exposure. That implies rotation periods of maybe minutes, possibly faster, and we have no mechanism for how an interstellar object would spin up to those speeds naturally. Then there's the other possibility, the one that gets whispered in late-night astronomy forums and occasionally floated by serious scientists who are careful to couch it in probabilistic terms. What if the symmetry isn't natural at all? What if we're looking at something designed? The word engine gets used. The phrase propulsive origin appears in papers. Because if you were building an interstellar spacecraft and you wanted to disguise it as a comet, but you also needed to maintain some kind of symmetric thrust system for course corrections, well, this is close to what you might see. A symmetric drive plume, a controlled plasma field, something that from a distance looks almost natural, but upon closer inspection reveals a geometry that nature doesn't typically produce. I know what you're thinking. That's a huge leap. That's the kind of speculation that gets scientists laughed out of conferences, and you'd be right to be skeptical. Extraordinary claims require extraordinary evidence, and so far, all we have are images showing unexpected symmetry. But here's the thing that makes this more than just wild speculation. The symmetry isn't the only anomaly. It's just the most visually striking one. Because when you start digging into the actual behavior of this object, the motion tracking, the spectroscopic data, the acceleration measurements, you find that the symmetry is only the beginning of a much deeper mystery. What we're about to explore together is a cascade of observations that don't quite fit. Each one individually could be explained away, but together they form a pattern that's forcing astronomers to reconsider fundamental assumptions about what interstellar visitors can be. We're going to look at the physics, the chemistry, the orbital mechanics, and yes, the speculation about artificial origins. Because whether this turns out to be an exotic natural phenomenon or something else entirely, 3i Atlas is already rewriting the rules. The question isn't just whether we're seeing a comet or a spacecraft. The question is whether we even know how to tell the difference anymore. When 3i Atlas emerged from behind the Sun on November 5th, 2025, astronomers at the R. Naves Observatory in Spain were watching. They'd been tracking this object since its discovery months earlier, predicting its trajectory as it swung through the inner solar system. Solar conjunction, the period when an object passes behind the Sun from Earth's perspective, always creates a gap in observations. You lose the object for weeks, sometimes months, depending on geometry, but you know roughly where it should reappear, and you point your telescopes at that patch of sky, waiting. The Naves team captured their first post-conjunction images in early November, and immediately something was wrong. Where was the tail? Every comet develops some kind of tail as it approaches the Sun, even faint ones. The solar wind and radiation pressure push gas and dust away from the nucleus, creating that characteristic streaming structure. 3i Atlas had shown clear cometary activity in earlier observations. There were images from September and October showing a diffuse coma, possibly a faint tail. The expectation was that activity would increase as it got closer to perihelion, its closest approach to the Sun. Instead, the November 5th images showed an object with no obvious tail structure at all. Just a bright central condensation with a roughly symmetric coma around it, but nothing streaming away. Avi Loeb, the Harvard astrophysicist who's become something of a controversial figure for his willingness to entertain exotic explanations for interstellar objects, immediately pointed out the strangeness of this observation. He'd been following Atlas closely, partly because it reminded him of Oumuamua, that other interstellar visitor that showed anomalous acceleration back in 2017 and 2018. Loeb had argued then that Oumuamua's behavior was potentially consistent with artificial origin, a claim that generated enormous pushback from the astronomical community. Now here was another interstellar object behaving oddly, and Loeb was taking notes. But Loeb didn't just note the missing tail. He'd been analyzing the trajectory data, the precise positional measurements that observers had been collecting for months, and he found something that elevated this from curious to genuinely puzzling. The object was accelerating, not just moving along its expected gravitational trajectory, but showing what astronomers call non-gravitational acceleration. There were two components: a radial component, pushing away from the sun, which is exactly what you'd expect if outgassing was producing a rocket effect. But there was also a transverse component, acceleration perpendicular to the sun line. That's harder to explain with simple outgassing models. Non-gravitational acceleration itself isn't necessarily shocking for a comet. We see it all the time. Gas jets produce thrust, and if those jets are asymmetrically distributed across the nucleus, they can push the comet slightly off its gravitational trajectory. The effect is usually small, but measurable. What was shocking about Loeb's analysis was the magnitude of the acceleration and what it implied about mass loss. Here's where the physics gets interesting, and I promise I'll make this as clear as possible, because it's crucial to understanding why this is so strange. When a comet accelerates due to outgassing, you're essentially watching a natural rocket engine. Material leaves the surface at high speed, carrying momentum. Conservation of momentum means the comet itself must gain velocity in the opposite direction. The relationship is straightforward. The mass of the comet times its acceleration equals the rate at which your ejecting mass times the velocity of that ejected material. It's the same principle that makes rockets work, just messier and less efficient. Loeb took the measured acceleration of Atlas and ran this calculation backward. He assumed a reasonable velocity for outgassing, something in the range of a few hundred meters per second, which is typical for sublimating volatiles like carbon dioxide or water ice in sunlight. Then he calculated how much mass per second would need to leave the surface to produce the observed acceleration. The number he got was enormous. We're talking about mass loss rates that would require at least 13% of the total mass of the object to be ejected over the observation period. Now, 13% mass loss sounds like a lot, but comets do lose mass as they orbit. That's what makes them bright. But here's the problem. If you're losing that much mass that quickly, you're creating a massive cloud of debris. Gas and dust expanding away from the nucleus at hundreds of meters per second, spreading out into a volume that should be easily visible. The cloud should be huge, possibly millions of kilometers across, depending on how long the outgassing has been active. And yet, in those November 5th images, there's no obvious debris cloud, no tail, no expanding shell of material that you could point to and say, there's your ejected mass. Loeb pushed the calculation further. If the acceleration is real and sustained, and if it's being caused by outgassing, then you can estimate the total mass of the object by working out how long it can sustain that rate of mass loss before it runs out of material entirely. His estimate came out to something like 33 billion tons, implying a nucleus potentially larger than 5 kilometers across. That would make Atlas a substantial object, much larger than initial estimates suggested. But a 5-kilometer nucleus losing 13% of its mass should produce a spectacular, easily observed cloud. We should be drowning in data about the tail structure, the dust composition, the gas emission lines. Instead, we have images showing a symmetric core with no clear tail. This is the paradox at the center of the Atlas mystery. The trajectory data says the object is accelerating. The acceleration magnitude, if it's caused by conventional outgassing, requires substantial mass loss. But the imaging data shows no obvious evidence of that mass loss happening. The expected debris cloud is missing. The tail structure that should be there isn't visible. Something in this chain of reasoning must be wrong, but it's not clear what. Space-based observatories have been contributing data as well. NASA's MAVEN spacecraft, normally studying Mars's atmosphere, managed to capture some observations of Atlas during its swing through the inner solar system. The Solar and Heliospheric Observatory, SOHO, which monitors the sun continuously, picked up the object in its wide-field cameras. These observations add to the dataset but don't necessarily resolve the paradox. They show there is some kind of coma, some material around the nucleus, but nothing proportional to what the momentum budget calculations suggest should be there. Online, the astronomy community is splitting into factions. Reddit threads devoted to Atlas have become battlegrounds between those who think we're witnessing something genuinely anomalous and those who argue we're just seeing normal cometary behavior from an unfavorable viewing angle. Some users are calling for more observation time, more data, systematic monitoring campaigns. Others are warning against over-speculation, pointing out that we've been fooled by apparent anomalies before, only to find mundane explanations once better data arrived. Loeb himself has been characteristically willing to float exotic possibilities. He's pointed out that the missing tail problem could be resolved if the acceleration isn't caused by outgassing at all. If something else is providing thrust, then you wouldn't expect to see proportional mass loss. The immediate question becomes, what else? What mechanism could accelerate a multi-kilometer object without producing visible exhaust? The natural answers start running out quickly, and you're left with increasingly speculative scenarios. Professional astronomers who aren't Loeb are generally more cautious. They point out that comet behavior can be wildly variable. Outgassing can shut off suddenly as active regions become dormant. Viewing geometry can hide tails behind the bright coma. Image processing can suppress faint extended structures. All of these are real possibilities that need to be carefully examined before jumping to extraordinary conclusions. But they also acknowledge that the observations are odd, that Atlas is not behaving exactly like a typical comet, and that it deserves continued scrutiny. What we're watching is the scientific process playing out in real time, accelerated by social media and public interest. Hypotheses are being thrown out. Data is being shared. Arguments are happening in astronomy forums and Twitter threads as much as in journal papers. And meanwhile, Atlas continues along its trajectory, seemingly indifferent to all the speculation it's generating. The question hanging over everything is whether the November 20th images, those symmetric plasma star photographs, represent a genuine shift in the object's behavior, or just a different perspective on something that's been strange all along. Did Atlas change, or did our ability to see it clearly finally catch up? And if it changed, what triggered that transformation? Why would a comet lose its tail and reorganize into perfect symmetry right as it's passing through the inner solar system, right when solar heating should be making it more active, not less? Those questions don't have answers yet, but they're pointing us toward the next layer of the mystery, which has to do with what this object is actually made of, and whether that composition is telling us something fundamental about where it came from and what it might be. Every comet carries a chemical signature, a fingerprint written in the light it reflects and emits. When sunlight hits a comet's surface, volatiles sublimate, turning directly from ice to gas without bothering with the liquid phase. Those gases fluoresce under solar ultraviolet radiation, emitting light at specific wavelengths that correspond to particular molecules. Point a spectrograph at a comet and you can read its composition, figure out what it's made of, get a sense of where and when it formed. We've been doing this for decades, building up a catalog of what normal solar system comets look like chemically. 3I Atlas is not normal by those standards, not even close. The James Webb Space Telescope, humanity's most sophisticated infrared observatory, turned its attention to Atlas in late 2024 and early 2025, capturing high-resolution spectra with its NIR spec instrument. What came back was immediately obvious to anyone familiar with comet chemistry. The carbon dioxide to water ratio was off the charts. Where typical solar system comets might show roughly equal amounts of carbon dioxide and water, or maybe favor water by a factor of 2 or 3, Atlas was showing carbon dioxide dominating by a factor of more than 7 to 1. 7.6 parts carbon dioxide for every 1 part water in some analyses. That's not just unusual. That's a completely different kind of object. Carbon dioxide ice is more volatile than water ice. It sublimates at lower temperatures. If you're building a comet in the cold outer reaches of a solar system or in interstellar space, where temperatures hover just a few dozen degrees above absolute zero, both water and carbon dioxide will be frozen solid. But as that comet falls toward a star and heats up, the carbon dioxide starts outgassing first, at larger distances from the sun, where water ice remains stable. Over many orbits, a solar system comet tends to lose its carbon dioxide, preferentially, becoming more water-rich over time. The fact that Atlas is so carbon dioxide dominated suggests it either hasn't made many close passes to any star, or it formed in an environment unusually rich in carbon dioxide relative to water. SphereX, another space-based observatory designed for all-sky spectroscopy, added its own observations to the pile. Its spectrophotometric data showed strong absorption features consistent with water ice, but also confirmed that extended carbon dioxide coma that Webb had detected. The carbon dioxide was spread out over huge distances, much larger than the visible coma in optical images. This creates a picture of an object that's furiously outgassing carbon dioxide, even while showing relatively subdued visible activity. It's as if the chemical action is happening in the infrared, in wavelengths our eyes can't see, making the object look quieter than it really is. Then there's the polarimetry, and this is where things get truly weird. Polarimetry measures how light is polarized, how the electric field oscillates preferentially in certain directions rather than randomly. When sunlight scatters off particles in a comet's coma, it becomes polarized, and the degree and orientation of that polarization tells you about the size, shape, and composition of the scattering particles. Every comet and asteroid we've studied shows a characteristic polarization curve. At small phase angles, when you're looking almost back toward the sun along the line of incoming sunlight, the polarization is slightly negative. As the phase angle increases, polarization crosses through zero and becomes positive, eventually reaching a maximum before declining again. A team led by Gray published polarimetric observations of Atlas on the R. Prashkev preprint server, and their results are unlike anything seen before. The negative polarization branch, that region at small phase angles where the polarization dips below zero, reached minus 2.7%. That's extraordinarily deep. Most comets and asteroids show negative branches around minus 1 to minus 1.5%. The inversion angle, where polarization crosses from negative to positive, came out at around 17 degrees. Again, that's unprecedented. Typical inversion angles for comets are more like 20 to 25 degrees. Asteroids can go lower, down to around 15 degrees, but Atlas is sitting right at the boundary of what we've ever measured, and arguably outside it. What does this tell us about the dust? The grains in Atlas's coma, the particles scattering sunlight and creating this weird polarization signature, must have unusual properties. The models that explain polarization behavior involve particle size, shape, and internal structure. Ultrafine grains, much smaller than typical comet dust, can push polarization behavior toward what Atlas is showing. So can grains with complex internal structures, maybe layered particles or aggregates of different materials stuck together in fractal arrangements. Some researchers have suggested exotic compositions, minerals or organics we don't usually see in solar system comets. Others point to surface roughness, or maybe unusual smoothness, as potential explanations. But there's another idea that's gaining traction, and it has to do with what happens to materials when they spend millions or billions of years in interstellar space. Interstellar space isn't empty. It's full of high-energy particles, galactic cosmic rays, protons, and heavier nuclei accelerated to nearly the speed of light by supernovae and other energetic events. These particles slam into any object drifting through the galaxy, penetrating the surface, breaking chemical bonds, creating new molecules through radiation chemistry. A recent paper by Maggiolo, Dughi, and collaborators explored what galactic cosmic ray processing might do to an interstellar comet. They modeled the irradiation of an icy surface rich in carbon monoxide, a molecule we know is common in molecular clouds and likely abundant in interstellar comets. Over time, scales of millions of years, the cosmic rays convert carbon monoxide to carbon dioxide through oxidation reactions. They also build up complex organic molecules, tholins, and other carbon-rich compounds, creating a processed crust that's chemically very different from the pristine interior. This model makes specific predictions. You'd expect to see a surface layer, maybe a few dozen meters thick, enriched in carbon dioxide and organics. Underneath that crust, the original composition would remain intact, whatever mixture of ices the comet formed with. Any outgassing we observe would be sampling this processed layer, not the core. This could explain the extreme carbon dioxide dominance. It could explain the unusual dust properties, if the grains being ejected are coated in or composed of these radiation-processed organics. And it suggests that what we're seeing might not represent the true bulk composition of Atlas at all, but rather a weathered shell hiding a different object underneath. The implications are significant. If Atlas's outer layers have been fundamentally altered by cosmic ray processing, then using its composition to infer where or how it formed becomes much more complicated. You'd need to account for the modification, work backward from the observed chemistry to the original state. This is possible in principle, but requires detailed modeling and assumptions about how long the object spent in interstellar space, what the local cosmic ray flux was during that time, and how efficiently the radiation penetrated and processed the surface. Some researchers find this model compelling. It provides a natural explanation for otherwise puzzling observations, and it makes testable predictions about what you might see if you could drill through the crust or observe freshly exposed material. Others point out that we don't really know how effective cosmic ray processing is over these timescales, that the models involve uncertain parameters, and that you could probably explain the observations with less exotic scenarios if you tried hard enough. But here's where the composition weirdness ties back to the symmetry mystery and the acceleration paradox. If Atlas has this processed crust, and if outgassing is coming primarily from that crust rather than the core, then maybe the outgassing properties are different from what we'd expect for a normal comet. Maybe the volatiles are being released in ways that create more symmetric distributions. Or maybe the crust itself is hiding something underneath, some internal structure or energy source that we can't directly observe because we're only seeing the outer shell. The alternative interpretation, the one that keeps getting whispered, is that the unusual composition isn't the result of natural processing at all. If you were designing an interstellar probe and you wanted it to mimic a comet, you'd probably give it an icy exterior. But you might not bother getting the composition exactly right. You'd use whatever volatiles were convenient, whatever mixture provided the properties you needed. The carbon dioxide dominance, the weird dust, the polarization anomalies. Maybe these aren't signs of a billion-year journey through irradiated space. Maybe they're engineering signatures, traces of a construction process that didn't quite match natural proportions. I want to be clear, the natural explanation exists. The cosmic ray processing model works. You don't need to invoke alien spacecraft to make sense of the composition data. But the composition data also doesn't rule out artificial origins. It sits in this frustrating middle ground where it could go either way, depending on what you assume about the underlying nature of the object. What we need is more data. Different types of data. Observations that can break the degeneracy between natural and artificial scenarios. And fortunately, as Atlas continues along its trajectory, opportunities for those observations are emerging. The object's orbit, its interaction with the solar wind, the structure of its coma and tail when viewed from different angles, all of these provide ways to probe deeper into the mystery, which is exactly where we're heading next, into the dynamics of this object's motion and the possibility that spacecraft, human-built spacecraft, might actually be able to reach it and find out what it really is. Every orbit tells a story, and interstellar orbits tell stories about the galaxy itself. When an object comes from beyond our solar system, when its velocity is high enough that the sun's gravity can't capture it into a bound orbit, that object is on what we call a hyperbolic trajectory. It falls in, swings around, and flies back out into the darkness, never to return. We've only confirmed a handful of these interstellar visitors. Oumuamua in 2017, Borisov in 2019, and now Atlas, the third such object, hence the designation 3I. NASA's trajectory data for Atlas shows it approached the Sun to a distance of about 1.36 astronomical units at perihelion. That's roughly the distance of Mars's orbit, well inside Earth's orbit, but not dangerously close to the Sun itself. Its closest approach to Earth came at around 1.8 astronomical units, which translates to about 170 million kilometers. That's not close in absolute terms. Earth-based telescopes need to work hard to resolve any detail at that range, but it's close enough for good spectroscopy, close enough for polarimetry, close enough to track subtle changes in brightness and position. The hyperbolic nature of the orbit means Atlas is moving fast. Objects on bound orbits exchange potential energy for kinetic energy as they fall toward the Sun, speeding up, then slow down as they climb back out. But interstellar objects start with excess velocity. They're already moving faster than escape speed when they enter the solar system, and they maintain that excess throughout their passage. For Atlas, this translates to a velocity relative to the Sun of several kilometers per second, even at perihelion. It's not lingering. It's passing through, and our window to study it is limited. But before it started showing that strange symmetric structure, before the tail disappeared in early November, Atlas was behaving more like a conventional comet, or at least more conventionally than it is now. Ground-based observations from the Tide Observatory in the Canary Islands captured images in late October showing a sunward carbon dioxide plume. This is actually somewhat unusual. Most cometary jets point roughly away from the Sun, driven by sublimation on the day side. But Atlas showed this jet extending toward the Sun, stretching about 10,000 kilometers in that direction. Sunward jets can happen. They're typically explained by topography on the nucleus. If you have a cliff or a crater wall that faces the Sun, it can focus outgassing in that direction, creating a jet that appears to point sunward when viewed from certain angles. The tidy observations suggested localized activity, active regions on Atlas's surface pumping out carbon dioxide in concentrated streams rather than uniformly. This fits with standard comet models. You don't expect uniform outgassing. The nucleus rotates, different areas receive different amounts of sunlight. Composition varies across the surface. Jets are normal. What's not normal is the subsequent evolution. If you have active jets producing visible plumes in late October, you'd expect that activity to continue or even intensify as the comet gets closer to the Sun. Solar heating increases with decreasing distance. More heat means more sublimation, more gas production, brighter jets, and tails. The standard expectation was that Atlas would become more visibly active through November and December as it swung through perihelion. Instead, the tail vanished. Amateur observers who'd been tracking Atlas reported a complex sequence of changes. Plumes would appear, then fade. Something that looked like an anti-tail, a tail pointing toward the Sun, caused by viewing geometry when you look at the dust sheet edge-on, appeared briefly. Then, the whole tail structure seemed to dim dramatically or disappear entirely, right around the time of the November 5th post-conjunction observations. By November 20th, when those symmetric plasma star images emerged, the tail was essentially gone, replaced by this glowing sphere. Some observers insist the tail is still there, just very faint, possibly overwhelmed by the bright symmetric coma. Others argue that what we're seeing is a true shutdown of cometary activity, at least in the visible wavelengths. The infrared observations suggesting ongoing carbon dioxide outgassing complicate this picture. Maybe the object is still outgassing vigorously, but the gas and dust distributions have reorganized into something more symmetric. Or maybe the dust production has dropped while gas continues, making the tail too faint to see against the bright core. The non-gravitational acceleration that Loeb measured from the trajectory data provides another piece of this puzzle. According to analyses posted on Reddit by users digging through JPL Horizon's ephemeris data, the acceleration vector is remarkably clean. It's not wandering randomly as you'd expect from jets firing in different directions as the nucleus rotates. It's steady, maintaining a consistent direction over time. The in-plane thrust component suggests the acceleration is happening within the orbital plane, not perpendicular to it, which again is slightly unusual, but not impossible for cometary outgassing. If you plot the trajectory carefully, accounting for the measured acceleration, You can extrapolate forward and backward, figuring out where Atlas came from and where it's going. The inbound trajectory suggests it originated from a particular direction in the galaxy, though pinpointing a specific source system is impossible given the timescales and galactic dynamics involved. The outbound trajectory shows it leaving the solar system on a path that will take it back into interstellar space, continuing indefinitely unless it happens to encounter another star system millions of years from now. This is where speculation about spacecraft observation opportunities comes in. Atlas is moving through the inner solar system right now, this month, this week. Various space assets are out there, missions designed for other purposes, but potentially positioned to observe. ESA's JUICE spacecraft, on its way to Jupiter, isn't really in a position to make a close flyby, but it could potentially observe Atlas from a distance, or sample the ion tail if the geometry works out. Other missions, satellites in Earth orbit, could contribute observations if tasked appropriately. The real prize would be in situ measurements. Flying a spacecraft through Atlas's coma or tail, sampling the gas and dust directly, measuring the plasma environment, looking for magnetic fields or electrical charge distributions. This is how we've learned the most about comets in the past. The Rosetta mission to comet Churyumov-Gerasimenko revolutionized our understanding by spending 2 years orbiting a comet, watching it up close through its entire perihelion passage. A similar mission to Atlas would answer so many questions, but mounting such a mission on short notice is essentially impossible. Spacecraft take years to design, build, and launch. Trajectories need to be calculated precisely. Instruments need to be selected and tested. By the time you could get a probe to Atlas, it would be long gone from the inner solar system, too far away and too faint to study effectively. The window for in situ exploration is closing as we speak. However, there are indirect ways to probe Atlas's environment. The solar wind, that constant stream of charged particles flowing outward from the sun, interacts with cometary comas in predictable ways. When the wind encounters the neutral gas in a coma, charge exchange reactions occur. The solar wind protons grab electrons from the cometary molecules, becoming neutral while the molecules become ionized. These newly created ions get picked up by the magnetic field embedded in the solar wind and carried away, forming the ion tail. The interaction region, where the solar wind meets the coma, can create a magnetic pileup, a region where the interplanetary magnetic field drapes around the obstacle created by the coma. If Atlas has a particularly dense coma, or if its outgassing creates unusual plasma conditions, you might see unexpected magnetic structures in the solar wind data downstream from its position. Satellites that monitor the solar wind for space weather purposes, spacecraft like ACE or DSCO-VR, or the Parker Solar Probe when positioned correctly, could potentially detect Atlas's influence on the solar wind flow, even without directly observing the comet itself. Some researchers have proposed looking for this signature. If Atlas passed close enough to one of these spacecraft, and if its coma was extensive enough, there might be a detectable perturbation in the magnetic field or plasma measurements. This would provide indirect information about the coma's density and extent, helping constrain models of the outgassing rate and composition. The tail dynamics, or lack thereof, remain one of the most puzzling aspects of the whole Atlas mystery. Tails are supposed to be straightforward. Dust particles leave the nucleus, get pushed by solar radiation pressure, and form a curved tail along the orbital path. Ions get swept away by the solar wind and form a straight tail pointing away from the sun. Both processes are well understood, modeled extensively, consistent across hundreds of observed comets. Why Atlas would deviate from this pattern, why its tail would essentially vanish right as it's passing through the region where tails should be most prominent, doesn't have an obvious answer. Unless the tail didn't vanish. Unless what we're seeing is a reorganization of the dust and gas into a different geometry, something more spherical, more symmetric. If the outgassing became uniform across the surface, if the rotation rate increased dramatically, if some internal process changed the way volatiles are being released, you could potentially create a symmetric halo instead of a directional tail. This would still be strange, still requiring explanation, but it would be a natural process, not necessarily indicating anything artificial. The alternative, which keeps nagging at the back of every astronomer's mind, whether they admit it or not, is that the tail vanished because the propulsion mechanism changed. If Atlas were artificial, if it were an interstellar probe using some kind of drive system, you might expect to see different exhaust signatures at different phases of the mission. Maybe the drive was off during the long approach, letting Atlas coast and look like a natural comet. Then, as it reached the inner solar system, the drive activated, producing thrust without the messy exhaust plume you'd associate with chemical rockets or outgassing. The symmetric glow could be the signature of an active drive, something that produces a controlled plasma field or directed energy without the chaos of natural sublimation. I know how that sounds. I know it's speculative to the point of science fiction. But the observations are forcing people to think in these terms, if only to rule them out. The scientific method requires considering all possibilities, even unlikely ones, and then using data to eliminate hypotheses until you're left with whatever explanation actually fits. Right now, both natural and artificial scenarios remain on the table. Neither can be definitively ruled out with the data we have. And that ambiguity, that uncertainty, is driving both serious scientific investigation and wild online speculation in equal measure. What happens next depends largely on what Atlas does over the coming weeks and months. Will the tail reemerge? Will the symmetry persist? Will the acceleration continue unchanged? Or will it vary in ways that reveal more about its source? Every observation, every new data point, either narrows the possibilities or opens new questions. And the community watching this unfold is learning, in real time, just how hard it can be to distinguish between the truly anomalous and the merely unusual. There's a specific rotation rate that would make an outgassing comet appear symmetric. You'd need the nucleus to spin fast enough that during a typical exposure time, maybe those 20-minute integrations that amateur astronomers use, the jets would blur into a uniform halo. Calculate the math, and you're looking at rotation periods measured in minutes, possibly even faster. For a nucleus several kilometers across, this means surface velocities approaching hundreds of meters per second. That's right at the edge of what an icy body can tolerate before centrifugal force starts ripping it apart. We know comets can spin fast. Some short-period comets that have made many passes around the sun have been spun up by outgassing torques. The same jets that produce thrust also create rotational acceleration if they're not symmetrically distributed. But we're talking about spin rates built up over decades or centuries of orbital evolution. Atlas is an interstellar visitor making its first and only pass through our solar system. It hasn't had time to spin up through natural processes. If it's rotating fast enough to create the observed symmetry, that rotation must have been there from the beginning, somehow imparted during formation or through some encounter we don't know about. The rapid rotation model has appeal because it's entirely natural, requiring no exotic physics. You just need a fast-spinning nucleus and reasonably uniform outgassing, and geometry plus exposure time do the rest. The symmetry becomes an illusion created by temporal averaging. Different observers seeing slightly different symmetry levels could be explained by different exposure times or different rotational phases during observation. It fits within the boundaries of conventional astrophysics, but it requires that high rotation rate, and so far we don't have direct measurements of Atlas's spin. Light curve observations, which track brightness variations over time to infer rotation periods, have been attempted, but the results are ambiguous. Some observers report seeing periodic variations consistent with rotation periods of several hours. Others see no clear periodicity at all. The lack of a strong, obvious rotation signal is itself somewhat strange for a comet this bright. You'd expect surface features, active regions, and irregular shape to create detectable brightness variations as the nucleus rotates. Then there's Avi Loeb's alternative framework, the one that's generated the most controversy and the most interest. Loeb has been explicit about his reasoning. He starts with the acceleration data, those non-gravitational forces showing up in the trajectory. He calculates the momentum budget, working out how much mass needs to be ejected, and at what velocity to produce the observed thrust. Then he looks at the images and sees no corresponding debris cloud, no tail structure proportional to the required mass loss. The conclusion he reaches is that conventional outgassing cannot explain the acceleration, which means something else must be providing thrust. What else could provide thrust? In the natural realm, you run out of options quickly. Outgassing is really the only game in town for cometary acceleration. Radiation pressure from sunlight can push on small particles, but for a multi-kilometer nucleus, it's negligible. Magnetic interactions with the solar wind are too weak. Gravitational perturbations from other bodies are accounted for in the trajectory models. If you've ruled out outgassing and there's nothing else natural that works, you're left staring at the possibility that the acceleration is artificial, produced by some kind of propulsion system. Loeb frames this in probabilistic terms, though he's careful to say the probabilities are subjective, based on incomplete information. Before the November observations, you might have assigned a very low probability to artificial origin, maybe 1 in 10,000 or less, just the base rate for exotic explanations. But each anomaly adjusts that probability. The strange composition shifts it slightly. The acceleration without visible tail shifts it more. The symmetric structure shifts it even further. Using Bayesian reasoning, where you update beliefs based on new evidence, Loeb argues that the cumulative weight of anomalies has pushed the probability artificial origin up to something non-negligible, maybe a few percent or higher depending on how you weight the various observations. Online communities have taken this framework and run with it. Reddit threads devoted to Atlas feature amateur Bayesian analyses where users plug in their own estimates for how likely each observation would be under natural versus artificial scenarios. Some of these analyses conclude probabilities as high as 68% for artificial origin, though these are based on assumptions that many would consider overly generous to the artificial hypothesis. Other users push back, arguing that the natural explanations haven't been exhausted, that we're pattern matching on incomplete data, that the history of astronomy is full of anomalies that turned out to have mundane explanations once we looked closer. The term engine hypothesis has stuck, though it's not clear exactly what kind of engine we'd be talking about. Chemical rockets are out. The exhaust plume from chemical propulsion would be obvious, and you'd still have the mass loss problem. Nuclear propulsion, fission, or fusion might produce less visible exhaust, but would generate signatures in other wavelengths, gamma rays, or neutrons that we haven't detected. Electric propulsion, ion drives, would be efficient, but produce very low thrust, probably too low to explain the observed acceleration for a massive object. That leaves more exotic possibilities. Solar sails could work in principle, using radiation pressure from sunlight for thrust, but Atlas isn't demonstrating the acceleration profile you'd expect from a sail, and there's no evidence of the large reflective surface that would be required. Laser sails, pushed by directed energy from some external source, face similar problems plus the additional question of where the laser would be coming from. Hypothetical propulsion systems based on physics we don't understand yet, warp drives or reactionless thrusters or manipulation of space-time are fun to speculate about, but are effectively untestable with current observations. What you're left with, if you take the engine hypothesis seriously, is something that produces thrust with minimal visible exhaust, operates efficiently enough to accelerate a massive object, and creates a symmetric plasma signature that could be mistaken for a natural coma. That's a very specific set of requirements, and it's not obvious what technology would fit all of them. Some researchers have suggested that the symmetric glow might be exactly what you'd see from a magnetic confinement system, something that bottles up plasma exhaust and directs it in a controlled way. Others propose that what looks like a symmetric coma could be the waste heat signature from an onboard power system, radiating in all directions. The problem with all of these ideas is that they're essentially unfalsifiable with the data we have. You can imagine a propulsion system that would produce the observed signatures, but you can't prove it exists. And the natural explanations, while strained by the observations, aren't completely ruled out either. Maybe there's some subtlety in cometary physics we're missing, some way that outgassing under unusual conditions can produce symmetric distributions and acceleration without obvious tails. Maybe the viewing geometry is fooling us. Maybe multiple effects are conspiring to make a natural object look artificial. Counter-arguments to the engine hypothesis exist in the peer-reviewed literature. A recent paper by Newcart employed detailed thermophysical modeling combined with Monte Carlo simulations to explore whether conventional volatile outgassing could reproduce Atlas's observed behavior. The model included realistic surface temperature distributions, depth-dependent composition, jets driven by pressure buildup under surface crusts, and the chaotic dynamics of rotating irregular nuclei. When tuned with plausible parameters, carbon monoxide and carbon dioxide outgassing from localized active regions could produce acceleration profiles similar to what's been measured, without requiring exotic physics. This is important because it demonstrates that the natural explanation space hasn't been fully explored yet. With enough complexity in the model, enough free parameters to adjust, you can fit the data using conventional comet physics. The question becomes whether you're fitting signal or noise, whether the complexity you're adding is justified by independent evidence, or whether you're just tuning the model to match one particular dataset. Newcart's work suggests the natural explanation is viable, but it doesn't prove that's what's actually happening with Atlas. It just shows it's possible. The philosophical implications of the engine hypothesis extend far beyond Atlas itself. If we confirm that this object is artificial, it would be the first detection of extraterrestrial technology, the first proof that intelligent life exists elsewhere and has mastered interstellar travel. That's a civilization-changing discovery. It would force immediate questions about intent. Is Atlas a probe? A derelict? An accident? Is it observing us or just passing through? Does it pose any risk? SETI, the search for extraterrestrial intelligence, has traditionally focused on radio signals, looking for deliberate transmissions from other civilizations. The idea that alien technology might reveal itself through anomalous motion of interstellar objects opens a completely different search strategy. Instead of listening for messages, you look for objects behaving oddly, for trajectories that don't quite fit gravitational models, for artifacts drifting through the galaxy. Atlas and Oumuamua before it have prompted serious discussions about how to systematically search for such objects and what criteria would be sufficient to claim artificial origin. Some researchers have proposed the term starshot detection for this approach, borrowing from the Breakthrough Starshot project that aims to send lightweight probes to nearby stars using laser propulsion. If we're thinking about sending probes to other stars, maybe other civilizations are too. Maybe the galaxy is full of these things. Interstellar probes launched millions of years ago by civilizations that might not even exist anymore, still following their programming, still gathering data, or carrying out whatever mission they were designed for. The statistics matter here. How many interstellar objects pass through the solar system? Based on detections so far and the known sensitivity limits of our surveys, astronomers estimate that several interstellar visitors pass within a few astronomical units of the Sun every year. Most are too small or too faint to detect. We only spot the larger ones, and even then, only if they pass relatively close to Earth or develop visible cometary activity. If a tiny fraction of interstellar objects are artificial, maybe 1 in 1,000 or 1 in 10,000, then we should expect to detect one every few decades or centuries, depending on our survey capabilities. Two potentially anomalous detections, Oumuamua and possibly Atlas, in less than a decade of modern surveys, is either a remarkable coincidence or a hint that artificial objects might be more common than we'd expect. But we can't just declare victory for the alien hypothesis based on ambiguous data and frustration with natural models. Science requires rigor, requires ruling out alternatives, requires independent confirmation. What we need are observations that would be very different under the natural versus artificial scenarios, measurements that break the degeneracy, imaging that definitively shows or rules out tail structures, spectroscopy sensitive enough to detect exotic chemical signatures, polarimetry across a wider range of wavelengths and phase angles, radio observations looking for any emissions that might indicate electronics or power systems. The International Asteroid Warning Network, a collaboration of observatories and space agencies focused on near-Earth object monitoring, has prioritized Atlas for continued observation through the end of 2025 and into 2026. Multiple telescopes are tracking it, collecting photometry and astrometry, building a comprehensive dataset. Polarimetric campaigns are ongoing, with the Very Large Telescope and Nordic Optical Telescope devoting time to measure Atlas's polarization in detail. These observations will either confirm the unusual properties reported in earlier studies or reveal them to be artifacts of limited data. What we watch for in the coming weeks is change. If Atlas is natural, its behavior should evolve in predictable ways as it recedes from the sun. Activity should decrease as solar heating drops off. Any symmetric structure should break down as outgassing weakens and becomes more irregular. The coma should fade, possibly revealing more about the underlying nucleus. If Atlas is artificial, the behavior might be different. The symmetric structure could persist. Acceleration could continue unchanged, or vary in ways that don't correlate with solar distance. New features could appear as onboard systems activate or deactivate. Every night, someone somewhere is pointing a telescope at Atlas, capturing photons that traveled across the solar system from this enigmatic object. Those photons carry information, encoded in their wavelengths and polarizations and arrival times. We decode that information, translate it into measurements and images and spectra, and try to build a coherent picture of what we're looking at. Sometimes the picture resolves into something familiar. Sometimes it deepens into mystery. And sometimes, very rarely, it hints at something we've never imagined possible. Atlas sits somewhere in that uncertain space, neither clearly natural nor demonstrably artificial, challenging our assumptions and forcing us to question how well we really understand the universe we inhabit.